Welcome back. Glad that you've joined us for this post in which we explore how we find solutions to the problems we've identified. This is the fifth video in a series of video posts examining diagnostic process mining. In previous videos, we've discussed how to define the problem, document our assumptions in a causal diagram, and estimate the causal impact. We've also examined how to validate the estimate using sensitivity analysis. We've used the data, real-life event data set from the Business Process Intelligence 17 event log, which documents the loan process for a Dutch financial services company to illustrate these key points. And you may recall, if you follow the video posts, that was the problem statement, lower than expected acceptance rate. However, the causal effect of our hypothesis, that is that chasing customers, repeatedly contacting them, negatively impacts acceptance, is small causal estimate. The question, though, is how do we identify solutions or interventions which have a more significant impact on acceptance rates? That's what we'll be exploring in this video. The techniques we'll be discussing were suggested in a paper published by a team from the University of Melbourne and Tartu in a paper entitled Process Mining Meets Causal Machine Learning, Discovering Causal Rules from Event Log. The link to the paper will be in the comment section, so if you're interested in reading it, I'll post the full link. We're going to follow a two-step process. First, we use action rule mining to identify a set of potential solutions, and then subsequently we'll use uplift modeling to find out those subset of cases on which the solution has the greatest impact. So let's look at that first one, action rule mining. What exactly is it? Well, action rule mining enables us to discover from our data a set of rules or actions which, when followed, will change the outcome of cases from an undesirable to a desired state. This set of actions are feasible because we recommend only changing those attributes that we are able to influence. Let's see how this works in practice using our loan data set. So we specify the outcome variable. In this case, we want to change the accepted from no, i.e. the loan was declined, to yes. That is the desired change, as it were. Then we specify what the stable attributes are, i.e. those attributes we are unable to influence. It's outside of a sphere of influence. So one of those is credit score. We then specify the flexible attributes, those that we have the power to influence. So for example, we can influence the monthly cost or the payback period of the loan. We also specify the minimum support for the rules. This is the minimum percentage of cases a rule should apply to. Finally, we specify the confidence, the minimum percentage of cases that will change outcome to the desired state, that is from declined to accepted, if those rules were followed. Let's examine the result set when we run this on our data set. The code, as you can see there, is what we've written in Python. That's fairly straightforward. It describes stable, flexible attributes and the desired change. The full code base, there's a link to a GitHub repository in the comment section that shows the full code base. Examine the results. Here is one of the action rules that are mined from our data set. There are 55 rules in total in that set. Let's walk through them. Let's interpret that result. So for the action rule says that for customers with a credit score of 0, extending the payback period from 100 to 126 months will increase the chance that they would accept the offer. This rule applies to just over 3% of all cases. That's the support. And for 28.4% of customers with a credit score of 0, the outcome will change if they followed the recommendation of the action rule. That's the confidence. We can also see there the uplift, and this predicts the incremental response of the action. In this case, 1.1% more customers accept. One point to make though, and that is that action rules are associational. They're not causal. We've discussed in previous posts the difference between associational relationships, variables, for example, that move in the same direction, and causal relationships, where one variable causes a change in the likelihood of another. And because of the associational nature of action rules, we look at uplift modeling to derive the causal links. Uplift modeling, as the name suggests, models the incremental impact of a treatment on a customer's behavior. So, in other words, if we do X, i.e., extend the client's payback period, how much likely are they to accept the offer? In other words, what's the incremental uplift from our intervention? However, as we mentioned in previous videos, we cannot observe counterfactuals. We cannot observe what happens when we extend the payback period and when we don't. We either observe one or the other, which is the reason that we use the average treatment effect, which looks at the effect of that treatment across the entire population. However, we established that this is a bit of a blunt instrument. It doesn't enable targeted intervention, hence the reason we focus on the conditional average treatment effect, which measures the effect of the treatment on a subset of the population. For example, in the previous video, we looked at subsetting clients based on their credit score. So uplift modeling uses this to identify whether for a certain subset of our population, implementing this solution will have a positive effect or a negative effect. It could also have a neutral effect, of course. So we illustrate this here. If we have a set of customers with a credit score of 0 and a payback period of 120 months, what happens if we extend that to 126 months? We specify the outcome, the solution, and the attributes that we would like to input into that uplift model. So let's look at the results of our uplift model. As is the case with previous code that has been written, there's a link to a GitHub repository in the comment section if you want to see how we derive this code. But we're going to focus on the results. The output from our model is an uplift tree, and this shows the uplift from applying the intervention to certain segments of customers. So looking at that tree, you'll notice that it's got a true false leg. The right leg is false. So that reads that if we extend the payback period for customers with a credit score of 0 and the first withdrawal amount less than 15,000, and obviously the upward amount greater than 42,000, then this will increase the chance that they will accept the offer. That is seen in that uplift score. Looking at the false leg, so extending the payback period for customers with a credit score of 0 and a withdrawal amount greater than greater than or equal to 15,000. True is the left leg. It will also increase the chance that they will accept the offer. But notice that the uplift score is less if we follow that branch, as it were, of the tree. So this enables us to apply interventions in a more targeted fashion to customers who are likely to respond, rather than a blanket intervention. We could also assign a cost to the intervention and calculate the benefit of intervening for a subset of customers. The question, though, is how do we validate those solutions and implement them? That will be the subject of our next video post. Hope you'll join us.